Hey everyone, my name is Sierra Moxon, and I'm a staff software developer at Lawrence Berkeley National Lab in Chris Mungel's group. And I'm going to be giving an introduction today to the linked data modeling language, or LinkML for short. Just to get started and to set our levels a bit here, I think we can all agree that if data in the biological domain was shaped more like this, with clearly labeled attributes and whole numbers and integers and units that were harmonized across all the different data sources, and everyone recording the same attributes and data properties as their compatriots were, then this data would be really easy to compare and ingest. But of course, in our world, data looks more like this. It's dispersed between many different resources with many different focuses. Sometimes documentation on sharing data is non-existent. We have a proliferation of identifiers for the same concepts, hundreds of thousands of named entities and terms, lots of free text notes, and the chain of provenance between these sources, where one resource might pull in several others and transform the data along the way with a variety of different methods for capturing that provenance change, really makes data in our domain difficult to collate. Quite frankly, much of our knowledge still exists in unstructured formats like literature, figures, lab notebooks, spreadsheets, but we do have a lot of standards that are trying to help. If I look on fairsharing.org, I think the statistic was taken last November, we do have greater than 800 open source FAIR databases that are trying to collate this information. And from BioPortal, we have over 900 ontologies. So things are progressing. And in fact, in the ontology development and reuse side of the data equation, we have a lot of interoperability and reuse going along. And we have a lot of great tools to help us with this reuse from the Obo Foundry and from others. So for example, HP uses the Kebi ontology and the cell ontology, and Go uses the sequence ontology. And we have tens of thousands of high quality curated knowledge annotations being entered every year into some of our resources. The gene ontology in particular is a model of success in capturing annotations consistently between organizations and knowledge bases, as well as developing a shared understanding and model of the concepts of biological processes, molecular functions, and cellular components. But what we found is that shared vocabulary terms are really not enough. Underneath that consistency is a schema layer that's not always designed for interoperability. A very simple example is on our screen now. I have two databases, completely made up example, each recording the metadata about samples taken from body waters in my home state, Oregon. Both record the depth and location information for these biosamples, but they do so in different ways that it currently requires a human, or more likely a few people with different levels of expertise to interpret the data. Even if these two tables are in the same database, there's nothing in the model itself that gives me the indication that they're both samples from Oregon, for example. And we see here that the environment in one table is a foreign key to another table, and in the other table, environment is a string. We need an object model or a schema or a data dictionary that sits outside of this technology used to be able to interpret this, and right now, oftentimes that's a human. To complicate matters, we also have many technology frameworks that we use to describe this kind of data that we collect, and the one we pick really depends on the hat we wear, what kind of research we're doing, what kind of technologies we're familiar with, and many of the same reasons you choose one data source or standard over another apply to technologies. Does the technology have a community of people willing to support it? Is the community moving forward towards a feature or benefit of one technology over another? Is it in active development? Obviously, all of these stacks have a learning curve, and the technology for our systems evolves just like biology does, and sometimes it evolves out from under the application using it. So right in the middle of all these languages and formats and specifications and ideas is the knowledge that we're all looking for, the real insights into climate change or patient health, and we need to figure out a way to get to that center ground. So clearly, the answer to all our problems is another standard. If you look at this lovely XKCD comic on the left, you start out with 14 standards. Why can't we just have one? The end of the day, now we have 15 standards. But the way we like to think about it in LinkML and in the modeling framework that we're developing is more like a universal converter box, where we use the benefits of other existing frameworks to their advantage and provide tooling to convert between them. So ultimately, LinkML helps different experts speak the same language. We call LinkML a framework because it not only has a metadata language and a model associated with it that all schemas written in LinkML conform to, but it also has an entire suite of tools that we make available to aid in drafting schemas, in validating and linting data conformant to these schemas, in converting between different model serializations. And by serializations, I mean something like writing your schema in YAML and being able to see it automatically generated in JSON schema, or writing a schema in JSON schema and automatically seeing it available as a SQL data definition language create table statement. So on the left, you can see the LinkML modeling language is made up of a few key components, classes and slots, for example. If you're used to another framework like a relational database, classes are analogous to tables and slots are analogous to columns, or in JSON schema, classes and attributes. And as an aside, the LinkML model itself is written using LinkML. So we definitely try to consume our own product here. And on the right, you see just a few of the many tools that we have available to help you validate data to your schema, implement best practices for writing a schema or generating code, Python classes or Pydantic classes, using your schema, even to the point of setting up data entry software that validates your data using your schema. But before we get into more detail with the tooling, we can take a look at some more meta model features with an example. Again, this follows the made up example of two different samples being taken in Oregon to see what kind of bacteria makes up a particular region of that body of water. So right now, if I'm capturing this data in plain old Excel or in a spreadsheet, I can see that I do have a model to my data, but right now it's very implicit. And with LinkML, we can make the assumptions we have to make about that implicit model very explicit. So in each row of this sample data set, I have, a bunch of attributes that I want to collect. Each has names and values and probably some expectations about what we can do for the values in that field. For example, can there be more than one value in this field? Can they be null? Can they be made up of ontology terms, or do they need to be made up of strings? And if you kind of look to the right here, I've kind of put together a small LinkML schema that shows off some of its key features. So right away, you see at the top that I've made a class called BioSample to group together all of the different rows of my spreadsheet into one sort of consistent object or table or class. Those are all sort of analogous in purposes of this discussion. Each BioSample has attributes or columns. And each of those columns or attributes can be further elucidated using LinkML. LinkML really loves ontologies. So here's two different ways I could use ontologies in my schema directly. One, I can say, let me set the definition of depth to exactly the same definition as the environment ontology uses for depth. So I'm going to set the URI for this parameter to be equivalent to this envo term, right? So in my RDF serialization of the model, those would be one and the same. For salinity, I'm going to say, well, I don't exactly want to use the URI for Pato to describe salinity, but it's exactly my definition, even though maybe I choose to define it a little bit different, exactly maps to the definition in Pato, right? For the bacteria column, instead of seeing just a comma here that may or may not be part of the name, I can actually set it to be multi-valued in LinkML. I can make the sample type required, so it can't be null. And I can even go as far as creating a dynamic enumeration in LinkML, where I can say, this particular field must be a value from a source ontology, like envo. So every value here must be from envo. And I just want to point out, I of course don't have enough time to go through all of the features in LinkML, but we do have a tutorial and it goes into great detail about all the different features that you can provide in your schema. And another really important thing here is that you can import your LinkML model. Your LinkML model can import other models. So if I have a LinkML model that defines a Pacific Ocean data set, and I have another LinkML model that defines, a Crater Lake data sample set, I can actually import the Crater Lake classes into my Pacific Ocean data model and use them and extend them to the best of my ability. And you can kind of see that we do that with LinkML itself. We're importing the types that LinkML defines. These are some things like query or string or int that LinkML itself defines. You're always importing those when you're making a new schema. So we have our data modeled in LinkML. We can also use the features of LinkML to help disseminate our model through our technical stack or provide for usage in different communities. And we've seen this kind of tooling help democratize schema development in that it lowers the barriers between technical and biological domain experts, helping them to develop a shared understanding and implementation of the shape of their data. So it also helps LinkML fit inside existing technical frameworks. For example, two of our flagship models, the BioLink model and the National Microbiome Data Collaborative Schema, both use YAML and JSON schema serializations of their LinkML model to exchange data. This doesn't preclude them from also representing their data in a SQL database or in a TSV or any of the other serializations that LinkML supports. And I think it's super critical whenever you have a model that there's documentation available for people that aren't familiar with the design decisions you've made to be able to interpret and reuse your work. And one of the added bonuses of LinkML toolchain is that out of the box, LinkML knows how to generate documentation. So each slot, and each class, and each entity in the LinkML schema can have a description, it can have comments, it can have notes, it can have exact and narrow and broad mappings, it can have a hierarchy of ISA relationships with other classes in the model, and all of that is formulated into documentation that's interactive, searchable, and visual. Okay. So would this even be a technical presentation if we didn't see at least a little command line output? Bear with me. But because LinkML has built-in generators that convert its schemas between serializations, we can easily produce a JSON schema and parasitize existing validation frameworks, i.e. a JSON schema validator for easy validation of LinkML elements. So LinkML does go a little bit further than simple JSON schema validation, as its meta model isn't simply a replicate of the JSON schema format, but it does produce easy to parse validation output. And this is really a current area of focus for our development of LinkML. We're moving towards a plugin architecture that allows, more custom validation. So for example, if you wanted to validate using Shex or Shackle and see the output of your validation, we're working towards a plugin architecture there. LinkML also has developed sort of a linting mechanism. So, and this component was added after adoption of LinkML by several people in several groups. And we noticed that while LinkML allows sort of a very flexible design for people to design their own conventions around naming slots and classes and enumerations, having an opinionated but configurable linting service really helped streamline our best practices. So now you can run the linter and see how your schema conforms to the best practices that LinkML has put together. Another area of focus for LinkML is helping to speed up the process of structured data extraction from text using large language models. LinkML provides a structured model and an ontological domain registry that instructs large language models in our tool called OntoGPT in extracting data from external sources. We did one recipe where we did one experiment where we used website recipes to create an ontology. And I just would encourage you to keep an eye out for Harry Caulfield's talk later in the week for more information on that use of LinkML. And of course, I don't have enough time here to tell you about all the features, but there are a lot of other modeling features and tools available from the framework. Some of the most interesting sit at the boundary between expertises. For example, we have a tool called Schema Automator that helps bootstrap a LinkML schema from a JSON schema or a TSV file. And we have a tool called Schema Sheets that allows schema development to happen not in YAML or JSON schema, but in a Google spreadsheet. And then we have tools that convert it to YAML for downstream use, which can be very helpful for people who understand very detailed decision-making about the domain itself, but maybe not the technology that you're using to implement that domain knowledge. So as I've alluded to already, LinkML is seeing a wide level of adoption already, and some of the same people that are driving the community for the Obo Foundry are also involved in making this a truly open space. It's welcoming and empowering, and we definitely favor an open data ecosystem. I think if you look at some of the tools we provide for setting up a new LinkML project, they sort of automatically encourage you to use GitHub and to make your schema available to everyone downstream. And I think it's an extremely important thing, even for us modelers, to be able to see what other people are doing in our domain and really try to reuse that work that they're doing so we can move forward on more discoveries. And I think from this early adoption and growing user base, we've sort of come up with a few key takeaways that I can share with you. One of them is that to fully develop all of the different serializations and all of the different features that we want from LinkML, we really need to encourage open data ecosystems and open development platforms. We really want to be able to get the input from a variety of experts, and at the end of the day, LinkML is a modeling language, and developing LinkML models takes the same kind of good communication and collaboration and compromise, iteration between modelers and developers and subject matter experts that all modeling requires. And we are really trying hard to develop a community of enthusiasts to contribute to this initial development effort. To that end, we support sort of a vibrant Slack community, monthly community call where we host tutorials and presentations from the community and discuss LinkML future plans. We also have a responsive issue tracker, and most of all, we really welcome everyone to join us in this effort because the dividends have been paying off very highly for the teams that implement it. We also want to encourage an examples forward design. As I said before, documentation is absolutely essential in encouraging reuse of a model. Domain-specific language can sometimes get in the way of comprehension. Examples work best for describing a complex model, and we've designed a framework tool called the LinkML Run Examples tool to encourage example-forward schema design. So this tool helps you kind of take an example bit of data, run it through a validator, see it in different serializations of the model. For example, if you're an expert in SQL, seeing how that data in JSON schema translates into the model in SQL could really help you understand how it works. It's also an incredible resource for people to understand how to submit or comply with a JSON schema or another kind of input system that uses LinkML behind it. Looking forward, LinkML is also experimenting with a transformer language. It's code quite similar to Flyway or Liquibase if you're coming from a relational model point of view. It encourages formalizing schema transformations and evolutions in a computable format as well. It's one of our lessons learned over many years of modeling data that modelers and developers should really encourage iteration. Shared understanding of modeling takes a long time. There's many nuances to our domain. We have different expertises within our communities. We have different definitions of model elements. Just ask a biologist and a chemist to agree on whether or not a gene is a chemical element or a genetic construct. We must write models that can change and evolve as our technical stacks and our understanding of the domain evolves. And while in development, we see sort of like potential of a transformation tool helping with both this kind of model iteration, but also denormalizing schemas into faster representations of the data. So I just really wanted to thank everyone for listening and for having us today, especially all the developers and contributors to LinkML. And I really just welcome you to reach out. You can contact me directly and I can get you hooked up with our community meeting or our Slack channel. And I hope to see you all out there soon. Thank you very much.